Good morning, good evening, and thank you all for being here. I am Vedant Khandelwal, and today I'm defending my dissertation, Neurosymbolic Methods for Retrieval, Reasoning, and Planning. And a big thank you to my committee for making the time on a compressed schedule and a lot of schedule changes. So here is the plan. First, the motivation and the thesis, and then one research question at a time. So RQ1 to RQ3 is what I've already discussed in proposal. RQ4 is the work that I've completed since, and it takes most of today. Artificial intelligence has always had two traditions: the symbolic, which writes the knowledge down, the rules, the concepts, and constraints. The advantage is that a person can read the system and check why an answer is allowed. The disadvantage is that it is correct only inside the cases its author thought of. The neural, where it learns from data instead, it handles noise, open vocabulary, and scale very well, but it cannot tell you why an answer is correct. Each is strongest exactly where the other is weakest. So the question is not which to choose, it is how to combine them. And neural systems today are genuinely strong. They pass medical licensing exam, predict protein structure, and solve Rubik's Cube on near optimal paths. I'm not disputing that. My point is narrower. None of them can tell you why a particular answer is right. And that becomes a problem the moment someone has to act on it. So, how do people combine symbolic structure with neural models today? Four well-known taxonomies, and each lists the places where symbolic structure can enter a learned system. One talks about 4 points along the learning pipeline. Knowledge infusion discusses three depths of infusion. COTS mentions six architectures, and the last one shows more than 15 design patterns. All four tell you where you can put symbolic structure. None tells you where you should. And side by side, they describe the same four positions in different words. Before learning, which fixes the model ever sees. At the input, which fixes what the request means. At generation, which fixes which outputs are legal. And after generation, which fixes what outputs are accepted. These four are not interchangeable. A constraint written into the loss cannot guarantee the property it encodes, but a check on the output can. So the field agrees on four positions. What is missing is a rule that says which one a given task belong to. So here are three tasks. One, a librarian searching the literature who needs a search another librarian can reproduce. A problem of graph coloring where a language model returns a coloring in seconds and this one is invalid. And planning where a learned heuristic solves the 15 puzzle under the four canonical moves. But the task that I actually care about is the same puzzle once the diagonal moves are allowed, and there the same heuristic fails. Nothing in those taxonomies that we saw tells me where symbolic structure should go in any one of them. In practice, people decide by precedent or by whatever model they already have, and neither is property of the task. So I define one property of the task, check. A check decides whether a candidate answer satisfied a stated criteria without having to construct that answer. A check can be exact. Two adjacent nodes can either share a color or they do not. It can be complete, like a test suit which catches some failures and misses the other, or it can be absent. No predicate decides whether a paper is relevant to a query. Paper is relevant at query time. I call this the correctness signal of the task, meaning a check can settle at what cost and whether the failure that limits the system survives it. That is the property of the task, not the application area. And then using that, we can clearly separate these three tasks cleanly. In retrieval, there is no check on the relevance at the query time. And what fails is the same query returning a different set of papers a month later. So symbolic structure goes in at the input. In reasoning, checking a coloring takes one pass over the edges while producing one is NP hard. So the check is cheap, and hence the symbolic structure goes after generation. In planning, every plan is already valid, and what fails is that the heuristic has seen too few move sets. So the symbolic structure goes before learning and again at the generation. Three tasks, three position, and what separates them is the check. And that brings to my thesis statement, where this dissertation asks where symbolic structure should enter a neurosymbolic system, one whose symbolic component fixes the admissible options and whose neural component only ranks within them. Four placements, one per check. Retrieval, where no check settles relevance at the input. Reasoning, where check is cheap but hard to satisfy after generation. planning where the check already passes and the coverage is limit before learning and again at generation, and applied settings where you would see more than one check per task. The placement follows from the correctness signal of the task, not from the application of that particular domain. So here, what we'll discuss today is part one that is already discussed in the proposal. I'll briefly go over that, and then part two, which is completed since, and it is this is where most of time will go today. So research question one, retrieval. How can curated concepts constrain what a neural retrieval model treats as relevant so that the same query returns the same results across run? So consider a librarian starting a systematic review and has to find every study that answers the question and miss none. This question, as shown in the slide, has two ideas in it: a diagnosis about HIV and a population related to foster children. And a paper counts relevant only if both hold. So I took that question to three research tools. Sight and Perplexity returned one, and consensus returned no relevant papers, missing on at least one of the two ideas. But the most important part is not that the numbers are low. It is that there is nothing here to check the result against. No predicate decides relevance at the query time. That judgment here belongs to the librarian. So this is clause one of my thesis. No check settles relevance. So symbolic structure enters the input. So for that, we put three curated resources in front of the model. None of them is learned. Mesh is the vocabulary PubMed itself is indexed with. So a mesh tagged query addresses the index the database was built on. UMLS links 200 vocabularies, which reaches terms the request never named but is relevant. And 1 to 3 Sentinel articles, which are papers the librarian already knows are on target. Together, they decide what may count as relevant. The neural encoder only orders what they already admit. So this is our architecture, and it runs in three major steps. Step one, vocabulary extension. Entity extraction pulls the concept out of the input query, and each one is looked up in the mesh hierarchy and expanded 2 levels down. And that expansion is then filtered by semantic similarity against the question and the Sentinel article. So only the branches actually on the topic survives. Step two is query expansion. Those concepts go to clinical BERT with a mass law, and it proposes terms never present in the query, but that belong to the same clinical context. Step three is retrieval and re-ranking against PubMed. And what the librarian gets back is the SQL PubMed search key itself. It is a conjunction, so every concept in it is mandatory, and a paper that satisfies only one of them never comes back, which is exactly the failure mode of the initial search that we talked about. It is an ordinary PubMed query string, so a second librarian can read it, check it, and run again. And then the loop closes at the top with librarian's review. So talking about results, more than a dozen academic librarian rated the top 5 results. On relevance, we are at parity, 36% against 38% with overlapping error bars. But on the design properties, our system is the only one that is reproducible, interpretable, and built on control vocabulary. Then the first query recall is measuring how many paper in the completed reviews final list were found by the first search. And across 20 completed reviews, our query found 92% compared to 88% for the librarian written query, while reducing the first pass from 8 to 15 hours that a human takes to under 1. So takeaway, the correctness signal forced the placement with no check available on the output. Symbolic structure had to enter at the input. The mechanism is the conjunction, and what the librarian keeps is a SQL query key that can rerun. Relevance is at parity, recall 92% against 88, and search time under an hour. And there is a real limitation for this. This needs a curated thesaurus and a database indexed against it, and it fails on anything they do not cover. So that is the first kind of signal where check is absent. Now research question 2 asks what changes when the task does have a check. So research question 2, reasoning, asks how can symbolic verification, targeted feedback, and selective escalation improve the correctness of what a language model generates on tasks where correctness is cheap to check and hard to construct. So in this given example, finding an answer is hard. Checking it is easy. So the graph coloring example that we see here, connected nodes must have different colors. A single pass over the edges verifies the solution and identifies any conflict, even though finding the coloring is NP complete. Debugging is similar. Test quickly exposes the failing case. Yet, Mistral, a cheap and fast LLM, always returns a coloring and never a valid one without noticing the conflict. Repeating the process also does not help. When GPT-4, a costly large reasoning model, is asked to explicitly check its own coloring, performance drops from 16% to 2, and longer reasoning does not close the gap. So the necessary check was cheap and available, but was never used. And that is clause 2. Symbolic structure enters after generation, when verification is cheap, but satisfaction is hard. So our solution, SOFAI-LM. SOFAI-LM is a metacognitive architecture built on thinking fast and slow theory by Daniel Kahneman. Instead of sending every problem to a large reasoning model, it tries the fast and non-reasoning model first. Every generated candidate solution goes to a symbolic validator, which returns accept or reject and exact violations or issues. And the next prompt carries that targeted feedback. So the model is repairing exact violation rather than guessing the answer again. The metacognitive part is the governance around that loop. The system watches its own progress, stops when the progress has been flat for 2 consecutive iterations, and only then escalates to the slower reasoning model under a cap of 15. So the symbolic contribution here is the validator, the feedback, and the governance, not simply the presence of a second model. Now, coming on to the experimental setup, here everything except the controller is held fixed. We consider 2 domains, graph coloring from GraCore benchmark and code debugging from debug benchmark, Python and C++ programs. So we consider 4,200 programs, each carrying an injected bug. The fast model or our S1 that we use here is Granite 3.3, 8 billion with thinking of. And the slow model is a reasoning model, which is DeepSeek R1 8 billion. And 3 further pairings of model reproduce the same results, what we'll see now. Same instances, same tools, same budget is used everywhere. And the 2 published baselines that we compare our work against is self-refined, where the model criticizes its own answer and what the validator found never reaches it. And pipe style loop, where the validator's violations are pasted into the next prompt, but the answer that produces them is not. So the overall picture here from the results that we see is our architecture, the LLM with metacognitive loop around it beats every baseline here on success rate and the time taken. So the metacognitive loop around it, LLM with metacognitive loop around it is marked as LLM at K. So here you'll see LLM at 5, LLM at 10, and LLM at 15. The baselines that we compare it against are LLM only, LRM only, self-rewind, and pipe style. 75, 76, and 79% against 64, 61, and 59 for the best baselines in each panel. And the point I want to land here is that most of these problems are solved even before we even escalate to the reasoning model. So on both debugging sets, Python and C++, the LLM at 10 iterations already beats every baseline, 63 and 60%, and it gets there faster than any other baselines do. And graph coloring does the same thing with LLM at 15. So this is another result that I find really interesting, and this is about the synergy. What is it that LLM at K has already learned, and how much of that is worth handing over when you escalate? So every iteration produces something, the attempts themselves and the validator's feedback on each one. So when the loop stalls and we escalate, we choose how much to pass on. The problem alone, the best attempt of the iteration, or the full history of iteration and the feedback. And the 2 domains answer in opposite direction. On graph coloring, where the constraint is global, the full history is actively harmful because a partly invalid coloring anchors the slow solver to infeasible structure. On C++ debugging, where the fault is local and sits in one place, the full history is exactly what helps because the earlier attempts here localizes the bug even more. So 2 contrastive results, and what separates them is whether the constraint is global or local. And the takeaway, the correctness signal force the placement again. The check is cheap and it names the violation. So the symbolic structure goes after generation. A cheap check with targeted feedback beats the bigger model outright, 73% against 14. And what the LM at K hands over on escalation has to match the constraint structure. One thing worth being precise about here is that deciding when to escalate is domain agnostic. It is just a progress signal. Deciding what to send when you do is not. And that is what the study pins down. The limitation is that it needs a validator that names the violation, and the validator itself cannot be the model. Research question 3 now asks what to do when checking is not the bottleneck at all. Research question 3, planning. How can symbolic domain generation supply the training diversity a learned heuristic needs to guide symbolic search in unseen planning domain? A quick word on what these problems are. So in planning domain, you are given a start state, a goal, and a set of legal actions, and you have to find the sequence of actions. That sequence is called a plan. Learned heuristics have proved very good at this, including problems with enormous state spaces, and on the standard 15 puzzle with 4 canonical moves, they solve it well. The task here is that same puzzle, once you allow the 4 diagonal moves as well, the estimate stops holding. So the network that solves the canonical version cannot solve this one. Nothing in it adapts. So it has to be retrained from scratch at a cost of days. And checking does not help here. Every plan the search returns is already legal. What is missing is not correctness, it is coverage. In a domain the heuristic never saw, the search runs out of time before it finds any plan at all. And new domains are hard to come by, as most of them are either written by hand, by humans, and even using language models only reproduce the ones they were trained on. And perturbing a domain at random without any parameters usually makes it unsolvable. So that is clause 3. The check already passes, but the coverage is our main limit. So our solution is PDDLFuse that generates a domain symbolically. It starts from existing planning domains as seed domains, combines them, and perturbs the action, their precondition, and their effects using 5 parameters. So what comes out is a domain nobody wrote by hand. The problem is built the same way. From a random initial state, it applies a sequence of actions and takes where it lands as the goal. So the goal is reachable by construction and the domain is never dead. It then validates by replaying the sequence and admits the domain only if execution actually reaches the goal. So every domain it emits is solvable, and that is what makes it usable as training data at scale. And the generation of these domains is controllable. The heat map on the right is solvability against the generator's parameters, and it moves predictability with them. So we can dial the difficulty instead of taking whatever the perturbation happened to give us using the parameters. Then the heuristic is then trained with reinforcement learning, where every data point is a PDDLFuse generated domains based on the seed domains and the problem, which is then converted into graph representation and fed into GNN, which learns to output heuristic estimates. The seed domains are held out entirely and never seen during the training because the only data that the model sees are the generated domains and never the actual original domains. And at inference, the heuristic sits inside a systematic search, which is the second placement at generation. The search decides what the heuristic is allowed to affect. It sets only the order of expansion. So a weak estimate costs time and plan length, never the validity. So the setup, our setup is on the right. The model is a graph neural network that we use here with 16-layer MPNN, trained for 1,000,000 iterations with a batch size of 1,000. And at inference, it uses batch-weighted A-star search. The 3 seed families that we test on are blocks, blocks world, N puzzle, and spanner planning domains, and are held out in full. So the heuristic never actually sees those original domains during training. The 2 baselines that are that I handed, those sees the seed domain directly. One is the fast downward, fast forward domain agnostic planner, and the goose, a supervised learned generalizable heuristic. So for each of the problems that we choose, we give a 600-second time limit per instance. So the claim being tested is coverage, and one heuristic trained only on generated domain, evaluated on families it never saw. And here, given the results, we perform at par or better than both the baselines. And on Spanner, where neither planner returns anything at all, we solve 11% of the instances. Again, to consider this solvability is in a constrained time limit of 600 seconds. So the takeaway, the correctness signal forced the placement a third time. The check is cheap and it already passes, so the coverage is limit, and the answer is symbolic generation before learning with a systematic search at generation. And it works. The seed families the heuristic never saw are recovered at 80, 72, and 11%. And the limitation is that the generator can only combine the structure what the seed domains already contain. So the dynamics and the different structure have to consider it as part of the training model. So that is there the three signals and three placement that we discussed from RQ1 to RQ3, taken one at a time. Now research question 4 is asking what happens when two of them land on the same task. So research question 4, composition. When an applied system fixes its admissible space at 2 points of the pipeline rather than one, does each placement still do the work it does alone? And we'll talk about this in two problem setting. Setting 1, so rocket assembly line. So consider you have 4 robots, a conveyor assembly, a rocket from 4 parts in a fixed order, where every later step depends on the one before it. A conveyor overheats, a tray jams, a grasp slips, and every step still to come is addressed to a factory that no longer exists. The stake is not small. Unplanned downtime costs the world's 500 largest companies about $1.4 trillion a year. Now, the validity is cheap to check here as well. What is scarce is the range of disruptions the system has ever seen, because a working line produces very few of them, and inducing them on the real equipment is slow, costly, and unsafe. That is the same shortage as research question 3 in a different setting, and the answer is same in kind. Write the fault dynamics down as executable symbolic transition code. Before we move further, let's go look at the prior works. So 3 group of prior work bear on this, and each supplies a single piece. Reinforcement learning for control, where faults sits outside the learning group. Detection and relational encoding, which identify a fault but not the dynamics of the disruption. And MDPs with action masking, where mask carries whole task constraint rather than an active fault. What they share is a split. A planner executes, a detector flags, a rule-based handler decides, and the planner resumes. So the recovery decision lives outside the policy that choose the action in the first place. Competence then grows only as fast as an engineer can enumerate faults, and the planner never pays for the fault it causes. So Rocket MDP is the simulator testbed. It mirrors the smart manufacturing rocket assembly pipeline here at USC. So here what we see is an 11 by 6 grid, 4 robots, a conveyor with ordered stops ending at final inspection, 4 components assembled in sequence and through discrete actions rather than continuous motions. And the reason there is this simulator at all is the shortest from what we discussed in the last slide, traces at controlled fault rates, none of it of a running line. So before we go further and talk about the faults, let's actually see how a complete correct run would look like. So again, as I mentioned, we have 4 pieces and the entire pipeline is there to assemble the 4 pieces. So here what we see is our first robot places the pieces on plate. Robot 2 takes those 2 pieces and brings it on its own place, goes to robot 3, which takes the base piece, takes the mid 1 piece from robot 2, places it on top of base, takes the mid 2 from robot 2, places it on top of mid 1, and places the top piece. You have the rocket assemble, which is placed back on the conveyor belt. So this pipeline, as I just discussed, is one complete correct run. It has no fault in it. So now that we have seen this, let's see what different faults that could occur. So here we have 4 fault families, and they are deliberately not variations on one thing. Each has its own trigger and its own required recovery. So no single generic fallback handles them all. Briefly, pick can fail, and the fix is to retry the pick. The tray can jam, and human frees it. A piece can be missing, and human replaces it. And a robot conveyor belt can overheat, and you wait through a cooldown. The probabilities on the tables are maxima. Faults rampant during training, and evaluation runs at the maxima. So two caveats that I just want to mention here: that detection is assumed. So what I measure is recovery given the fault is detected, and not detecting the fault itself. And the mask does not reveal the recovery. So even when I say we'll be masking the action, I'm not masking the actions and giving it directly. The only option is the recovery action, but it gets 6 to 8 actions stay valid even when a fault is active, including the recoveries that belong to other families. So this slide is sort of for discussing the exact placement. So let me try to go a bit more detail in this. So in the transition, each fault family adds a probabilistic branch, and the full outcome distribution is enumerable, which is what later lets sample learning and enumerated backups run on one model. In the state, fault type, location, and timer are explicit fields. 22 of the 55 dimensions, and the state carries the diagnosis, but never the actual remedy. Both of those enter before learning, and in the action set, the recovery action sits alongside the nominal ones, and one masked head ranks them together. That is at the generation. And the reward closes the loop. A minus 50 for triggering a fault propagates through the Bellman updates. So the cost of a fault reaches the rule that selected the action. Now here we'll quickly go over the algorithms and the models that we use. So 6 learned policies, and all 6 consumed the same fault model. So the comparison is fair. Same state, same action, same exact information. 2 are value based. DQN learns what each action is worth by trying things and remembering what happened. So it learns from samples. AVI is the model based one because we wrote the fault dynamics down. It reads the branches straight off the model and computes exact expected value instead of sampling. That is the neural insight symbolic arrangement in industrial form. The other four policy gradients are policy gradients, and they answer a different question. Does the representation matter? All four trained the same way with PPO. We roll out episodes, score each action by how much better than average it turned out, and clip updates so the policy cannot swing far in one step. The head is mass softmax over the valid action, so an illegal action never gets any probability at all. What varies is what feeds the head. PPO over the flat state vector is the baseline. ASNet has no fixed output layer. It scores each grounded valid action through a bilinear compatibility between state and that action. So the head follows the action set. The two graph network treats state as graph over robots, location, parts with typed edges. WMPNN aggregates messages separately per relation through weighted edges, and RGAT attention weights them so it learns which neighbor actually matters. And the fault indicators goes into the graph readout as well. So no policy sees anything less or more than the other. Now, talking about results, so all the four families that we discussed are active at maxima, over 60 episodes per method and 200 scored fault activation. Success rate is not what separates these methods. So if you see the graph on the left, all 6 complete 55 to 60 of 60 episodes, and most of them carry a fault. So completion is already close to a recovery rate. Where they differ is the recovery quality. AVI reaches 86% first recovery action accuracy against 79 for DQN. And it resolves faster, 2.7 steps against 3.2. Uniform random stays below 5%, so we know that the task is not trivial. And the scripted baseline reaches 100% too, where every fault is enumerated in advance. Handwritten rules are entirely adequate. So which is why the informative test is this one. I introduce a fault the system has never seen during the training, a collision between two robots in the handoff zone. And the correct response to that is halt, which was available throughout the training. So the action is not new. What is new is the trigger. and I make 3 localized changes, edits, and nothing else. So these are done only in the simulator, nowhere in the model or any of the system, the planners. A collision branch in the transitions, a mapping into existing state attributes, and a validity rule. Every learned parameter is frozen and nothing is retrained. And with that, AVI reaches 89% and EQN 84%, while the scripted handler, which has no rule for this because this is a completely new fault, falls below 10. So a trained model here clearly shows that yes, it can generalize across unseen fault as well. So for setting one, the correctness signal forced both placement, validity is cheap to check, and it is a range of disruptions that is undersample. The fault transition enter before learning, and the recovery actions enter the valid actions at generation. All 6 policies complete the task with every fault family active. So the interface is learnable, and the gain is reused under a change trigger. A collision the model never contained became an edit of the model rather than a new control path. The boundary is that a small fixed fully null fault set is exactly where a rule engine is cheaper, but otherwise the learned one would perform better. So coming on to our second applied setting is industrial asset assistant. So this is setting two, and it is a different kind of check. An agent is given a maintenance request in plain English, and it has to answer by calling tools on real industrial equipment. So here is one of the 139 requests in Asset Ops bench. Check if chiller 6 has any anomalies and create a work order if maintenance is needed. To answer that, you need to know which chiller this is, what its telemetry says, whether that count as an anomaly, and only then the ticket. And current systems are neither reliable nor cheap. The strongest published configurations complete about 65% of the task, with 6% of its statements unsupported. Now, there are two checks available here at two different positions. At the input, resolve which chiller this is, and after generation, ask whether it actually established what it claims. Two placements, one trajectory, and one shared budget, which is what lets me remove each in turn later and measure how good those are. So let's first understand what exactly is our task. It is to turn one maintenance request into an answer grounded in the plant's own data, where the request calls for it into a work order. No agent is named in the request. The system has to work out which ones it needs and at what order. The 5 agents that we have available here are IoT agent, which retrieves the metadata and sensor observations. TSFM agent detects anomalies over the telemetry. FMSR agent maps symptoms to probable failure modes. Work order agent creates queries and updates work orders. And rule logic agent runs the policy and constraint check. So a recommended action compiles with operational and safety rules. 99 scenarios are routine, where one agent and short tool trace is only required to solve it. And there are 40 that are incident, require several agent calls. So the check available here is resolution. Does the phrase in the request name a real thing in the plant, a specific asset, a site, a sensor? That is decidable by lookup, and it has to be settled before the plan is written. So exactly as in research question 1, the structure goes in at the input. The artifact is a knowledge graph, and it does two jobs. At planning time, the chiller on the north loop resolves to CH006 on site plant B with sensor CH6 temp01, and those identifiers go into the prompt. So the planner works from a stable domain context instead of a surface string. At verification time, the same layer exposes the constraints and the value ranges, and those go to the verifier. So failed check is rather exact rather than judged. That is why a graph and not a vector store is used here. One artifact that gives planner a referent and the verifier a rule. So going on to existing works, there are 6 lines of prior work, and every one, the question is the same. where is the decision to verify or escalate taken. In tool orchestration, it is not taken anywhere. In reasoning and acting loops, the feedback is task-specific scaffolding, not a verifier you can swap. In self-correction, the model critiques itself, whereas here the signal comes from outside. In external computation verification, the pattern is fixed in advance rather than decided at runtime. And meta reasoning gives us cost allocation, but here the budget is shared with a grounding placement on the same trajectory. So the contribution is the governance layer itself. So this is the solution architecture that we propose. The architecture going from left to right, you get a task instance that goes to S1, which is an fast LLM, which plans and synthesizes the answer. Before it plans block 5, the knowledge and constraints, hands it the resolve identifiers. S1 then produces a plan, and the tool and agent hub executes it against real agents. What comes back is a candidate solution. That goes to block 3, the solution evaluator, which grades it and returns which dimensions failed. That is the adjudication placement. If everything passes, we are done, and the trajectory is then logged into episodic memory. If not, we reach to two decision options. Has the iteration limit been reached, and is there still an improvement trend? If there is progress, the new prompt generator writes the next prompt around the failed dimensions as targeted feedback, and S1 tries again. If progress has stalled or the iteration cap is hit, the instances escalate to S2, which is a large reasoning model, which plans through the same hub and is graded by the same evaluator. So here our S1 is Granite 3.38 billion without thinking, and S2 is DeepSeek R1 8 billion with thinking. And the block 6 feeds accepted trajectories back into back as few shot context with no extra training. So grounding enters at block 5, verification and escalation at the evaluator, and both act on one trajectory under one budget. So talking about the experimental setup here, 139 published scenarios, identical hub access, 3 systems. First one is S1 only. So here S1 only, it plans a step, executes it, looks at the result, and replans from there, one step at a time. Second, S2 only, the slow reasoner from the outset. Third, a full system. And here, two details that matters are the verifier does not hand back a pass or fail bit. It returns a more targeted feedback, and we'll talk about it in the next slide. And here escalation is cost aware, and S1 call is cheaper than an S2 call in both time and compute. So we keep retrying while failure count is falling, and escalate after consecutive iterations with no improvement, or at the cap of 15. The last panel is what I compare the 3 systems on: reliability, which is the first try success, the hallucination rate, efficiency, which is tool steps and end-to-end runtime, and selectivity. So about the evaluator, there are 6 dimensions are graded, and each one of them is binary. So the criteria is on the slide beside it. Was the request actually answered? Do the reported values match what the tools returned? Are the claims backed by evidence that was actually executed? Were the agents called in a valid order? Is the answer readable? And is there anything asserted that the trace does not support? Success is strict. All 6 of them must pass. And the grader here is exact where it can be, with graph backed constraint checks and real execution outcomes. And the model graded on 2 out of the 6. That is the real limitation here. We use here the grader from the benchmark repo and held fixed across all the 3 systems. So there was no change done in the grader and the evaluator here. And the gains fall where the trace is observable and on result verification and agent sequencing. So that's where we actually know that it's not performing and it just looks plausible, but it's incorrect. So a quick work scenario of how this would look like end to end, because this would show what the verifier actually does. So on the first attempt, S1 plans 3 steps for a given problem. IoT agent retrieves telemetry, TSFM agent detects anomaly, work order agent drafts the ticket. A spike is found and the ticket is drafted. Data accuracy passes, hallucination passes, but the agent sequencing fails. So only the ordering signal is live. That signal selects the message the next prompt is written against. A ticket was created without a diagnostic step establishing a probable root cause. Notice that it does not say, it names the deficiency, not the remedy. It does not name the missing agent. On the second attempt, S1 replans, infers from the tool inventory, that the FMSR agent supplies root cause retrieval, gets bearing wear back, and rewrites the ticket with a grounded diagnosis. All six pass, and because a dimension was recovered, the stagnation counter never advances. So the slow model is never invoked. So here are the results over all 139, and the headline, here is quite simple. Against the agent, it wraps the same backbone with no verification and no escalation. First try success goes up on both scenario classes, and hallucination is roughly halved. And it takes fewer tool steps and less wall clock time to get there. So more reliable and faster at the same time. Against always on slow reasoning, I read success as a parity. What differs here though is time, because the slow model is invoked on a small fraction of the scenario, and against the strong published configuration, we match it on task completion at roughly half the tool calls, though not on hallucination, and that is 8 billion fast solver being compared to GPT 4.1. Coming on to the ablation, and this is what answers the research question 4 rather than asserting it. So removing grounding, and the system still completes the task, but it claims stop being grounded. So hallucination rises sharply. Grounding is load bearing for groundedness, which is exactly what is there to supply. So remove the diagnostic verifier, and it is worse on every axis. Success falls, hallucination rises, and escalation jumps, because without the decomposition, the cap is the only route to slow model. That system lands below one shot baseline, and matched attempt against blind self refinement. Verifier guided still wins, so the gain belongs to what the feedback says, not to more attempts. So setting 2, in summary, the correctness signal here is partial. So 2 placement acts on one trajectory, grounding at the input, verification after generation. They serve different failures and do not compete, and removing each in turn is what shows that each of the placement is load bearing. It is also not specific to this benchmark. We also tried it on MCP bench, and it lifts from 0.41 to 0.48 while cutting the number of tool calls. And the boundary matters. So here the check grade calls that have already run. So this is a triage under human review, not a complete autonomous controller. So that was the main part. Now let me close it with a quick key takeaways. So 5 key takeaways across all the studies. First, the claim, where symbolic structure attaches follows from the correctness signal of the task and not from its application domain. What repeats is the direction each signal predicts. Second, 3 method, at one at each position, and each beats a purely neural baseline. Third, applied settings present more than one signal at a time, and the placement compose rather than compete. Fourth, removing each placement in turn is what shows it is load bearing. And fifth, the rule is falsifiable, but on a new task, it names a placement, a benefit, a failure mode before anything is built. On future work for retrieval, so today what we saw is one search key per pass, and the librarian's assessment never actually reaches the next key and never used to update it. A key per turn would carry it forward while staying reproducible. For reasoning, a learned router would choose whether to iterate again or escalate. And the validator does not move here. The symbolic part remains as is, because it still decides acceptance and identifies violations. For planning, leave one family out generation is the next step, and moving the evaluation beyond puzzles to maybe quantum circuit synthesis, which has discrete action space and a check against the target. And for composition, the open question is the cost of revising the symbolic part held outside the learned policy. A change then becomes an edit rather than a training run, and then it can just comply with it at inference time. So this is the work now. Quickly about my PhD journey. So first, a huge thanks to my committee. Thank you, truly. I mean, this would not have been possible without any of you. And thank you for taking it on a very short notice, for reading the draft, sending comments, and for accommodating multiple changes to the schedule. I do want to thank Dr. Venkana. He was my undergrad advisor and who was the person who introduced research to me and gave me a path into it. I wrote my first ever research paper with him. Then to my advisor, so this is an image from 2019 where Dr. Sheth gave me a chance to come here to University of South Carolina as a research intern and see what PhD actually looks like. And that turned into PhD, being a PhD student and everything since. So thank you so much, Dr. Sheth, for believing in me, for supporting me, and for the guidance throughout this journey. So IBM Research was my only industry internship or my only internship throughout my course of PhD. Dr. Horesh, Dr. Rossi, Dr. Murugesan, and Dr. Patel, they taught me to see a problem for an industry perspective. So thank you so much for all the support, all the guidance, the chance to collaborate, and for advocating my candidacy always. And thank you for making my internship experience memorable. I do want to thank everyone here at AIC who was here and who is here, and AIC became like a second home. Every paper, every argument taught me something, and thank you so much, everyone, for all of it. Thanks to my family, who is the backbone for all of this. My parents, my late grandparents, my brothers and sisters. Thank you for your blessings and for being there every single time, for being, okay with the long distance and for putting my choices above your own. My friends from undergrad. So this is now over 10 years when we took this image, and we are still studying together for 10 years. Vishal and Bharat, above all. So I don't think I would have been able to do any of this without them. And of course, my seniors from undergrad and my close friends. Thank you all, like all of you. And last but not the least, my cats, Coco and Beans, who are an important part of the whole journey and my life now. And they had never had any interest in a single paper deadline or any deadline. And they were right not to. Here are the research presented today was supported by 3 NSF grants by University of South Carolina and by IBM Research. Thank them for supporting it. Here are my publication 2025, 2026, and 2024 all the way back to 2021. Here are some of the tutorials, labs, talks, panel seminars, and everything. And here are 2 issued patents and 1 award. Thank you, everyone. Open to questions.
Well, thank you for the detailed presentation. It was fast, but you said a lot. So you had a lot to say, I think, and you said a lot. So let's open the floor for questions of a general nature from everybody, including the audience. The audience in room is small. The audience online is large. So let's see whether anybody has questions from anywhere, and then we'll have more specific questions from the committee. However, if the committee wants to start asking questions now that are for everybody to hear, that's fine too.
Just to quickly remind, so one of the committee member, Dr. Rossi, at 10, yeah.
So we do have a time constraint. Who wants to start? Maybe the audience member here, the two audience members here have any questions? No, no questions from the audience here. Let me see in the chat. So I see some positive comments, but no question yet. Okay.
I can start.
Thank you, Dr.
Okay, thank you, Vedant. Thank you for the great work, for the very nice presentation. So I have two questions. One is, so you chose three domains, retrieval, reasoning, and planning. Do they cover everything that can happen in any task, or is something missing and is not covered by retrieval or reasoning or planning? That's the first question. And the second question is, okay, you showed us that if you have a specific, you call it the correctness signal of a task, then the combination of symbolic and neuro should be done in a certain way, and symbolic can be placed at the beginning, at the end, in the middle, or whatever, no? So depending on the correctness signal. But who decides this correctness system? Can you build an overarching AI system that takes a task, recognizes the correctness signal, and then builds the architecture in a way that is suitable for that correctness signal? So otherwise, it seems like it has to be done manually to recognize the correctness signal and then to use the right architecture. So can it be done automatically? Can an AI system be trained, or an LLM or whoever, used to recognize the correctness signal?
Right. So thank you for asking the questions, Dr. Rossi. So I believe retrieval, reasoning, and planning covers most of the different, possible combinations that we see in day-to-day lives. But again, as I mentioned in the takeaway slide for all the research question, the scope of what I discussed within reasoning, within retrieval, and within planning is limited. So what I've discussed today, would that cover every possible thing? Probably not. I'm guessing there are a lot more changes in the task and the character signal, and there can be a lot more variations. But overall, if we just want to say retrieval, reasoning, and planning, I believe that covers many of it. Again, not all of it. Coming on to the second question that you have. So I think the check itself is, as I mentioned, it's always task dependent. So for something like, if I just want to take an example from my dissertation here, for let's consider planning. Planning here, we know there are multiple checks that can be available. One check is the plan correct or not? Because that's what we are essentially trying to find. That's our goal. So yes, the plan is correct and that check is available. But then our another goal is, can it generalize? Can it go and handle multiple domains that it has never seen? So that's where we identify, okay, when we are trying to find the generalization, it cannot unless it has the coverage. Right. Same thing if we want to go about reasoning, we say, okay, we give it to any of these existing models and it can give you an output. And that output might look plausibly correct, like LLMs today can give you an answer that, looks correct, but it's not. So then the idea is, if you have a possibility of computing a correctness signal that is cheap, not expensive compared to, actually solving the problem, can you use that? So that becomes a correctness signal. The correct answer, whether the answer is correct or not, does it satisfies all the constraints that the input question asks for? Now, coming on to, can you train a model? Yes, you can train a model. I believe you would have to build some sort of data generator that can generate all these different possibilities of checks and tasks. Tasks are already there. You have lots of tasks already there, but computing it to checks, again, not completely manually, but through a set of defined rules. What is the final output? Is final output the main goal? Is the intermediate steps the main goal? Is coverage the main goal? Is the final output that an only human can review is the main goal? Then there is, no check available. And we go back to RQ1, that is the grounding. So that's sort of my answer. Does that answer your question?
So, but if you had to say, okay, so now I'm given a task, I want to recognize its correctness signal, because depending on that, I will use the right combination of neuro and symbolic,
Mhm.
right? So now I'm just in the pipeline, I'm just juxtaposing at the beginning an additional task, which is recognize the correctness signal of the problem that I've been given. What kind of task is that? Is that reasoning, retrieval, or planning?
That would be a reasoning task. It's yeah.
Okay. Okay. So then you would use for that task, recognize the correctness signal of task. You would use the architecture that you put in place for reasoning, I guess.
Yes, yes, you can use that architecture certainly. But again,
Okay.
you can only then compute the correctness signal of the task. As I mentioned, the scope is limited to the problems where you have a cheap verifier compared to the solver of that particular problem. But if that satisfies, then of course you can use SOFAI.
Okay. Thank you.
Thank you, Dr. Rossi.
Yeah, I do have a few questions, but I don't know what is the right order.
Well, just fire out.
Okay, so first of all, a truly admirable way to position and the question of which architecture typically is being asked, and you ask actually what can be checked. And I think that this puts a lot of things in the right place. And rather than having a zoo of architectures, you have a single question that I guess any person can ask working with AI systems. And you showed very nicely how you back the answer with working systems from mental health retrieval to rocket assembly. So that's really beautiful. So one question, it is related to Francesca's question, is when you think about the economy of computation, right? So currently when we look into the price of using S1 solver, I believe you had the one in slide 45 or so, and S2 cost call was costing something like 3. But the controller never looks at the price. It escalates when the progress simply stalls. Now, it may make sense to incorporate some sort of utility of, is it really worthwhile for me to invest, especially in I guess, and this is again a point that I saw in your last slide, you mentioned quantum computing, circuit synthesis, and this is one example where actually the check ladder tells you that the verification is very expensive. When the checks are cheap or absent, right? It is one story. But when they are expensive, we enter a different domain, right? And the economy changes, right? So how would you maybe suggest incorporating expensive verification or at least accounting for the economy of employing different solvers in the meta level decision? This is one question.
Right. Thank you for asking, Leo. So I think I'll answer it in two different parts. For and this is again based off my best understanding. For a problem where you have verification that's quite expensive, but that's the same case for actually solving the problem, then I think the task goes towards another subtask. Is if you just think about the verification part, can you make it approximate? Can you approximate the verification now instead of going with absolute? And that would be one way to handle it within the same architecture, as we mentioned. Then talking about the second question, right? Sorry, I forgot the second question. What was the second part?
No, I think you answered on both. I have another big question. So I like your answer. I think that makes a lot of sense. And again, that relates to Francesca's question about potentially having learnable checkers, right? So that would be one proposition to do that. The other big question from my end is, and maybe this is something worthwhile in the exposition, people from the RL community would say, look, effectively, aren't you doing some form of multi-agent RL? They would, they can state, look, you effectively have the environment is your checker, your agent is the solver, and then on top of that, you have some metacognition, which is really the RL algorithm. Now, there are a few distinctions, right? And we have to be clear about it, right? So one is the feedback content, which is much richer in what you do compared to RL, which where just a scalar is circulating back and forth. The adaptation also happens in a different place, right? The RL would make the updates across different episodes. With SOFAI, you actually do an in-context correction, right? Which is much more intrinsic and maybe more controllable, right? And the last thing is, again, related to the question we asked, the economy, so the query cost and safety, I guess in RL, often you have environments that are very expensive. You need to run a full-blown simulation or something of that sort. And here we actually assume that typically the checks are not very expensive. So the question I would like to ask you is there anything that we should adopt in SOFAI or other such systems, such as maybe the value of information exploration for escalation or something like that, and take from the RL, or should the RL community take something from what you propose here?
So thank you for asking that. I think the first part is sort of easy to answer. That's one of the future work that I mentioned. So I think one important part of SOFAI architecture as a whole is right now we are only looking at it from success rate in time. But if you want to increase the number of dimensions, it can increase to the compute, the dollar value of actual API calls and all those things. So now as you increase parameters, if you try to write all of those by handwritten rules, it's gonna break. There is only so many parameters and combinations that we can assume. So that's where, again, not replacing the actual validator, which can verify that still remains symbolic, but that can be replaced by a learned policy that then decides, given an input model and the different parameter preferences. Like maybe I say, I'm okay if it's not as 100% accurate, but I want to get it done in less than 10 seconds. So that's when I'm just looking at iterating with S1 and never escalating to a reasoning model, because that's much more costly. So learning this policy through RL is something that would help and make it more easy to overall expand to more parameters than just considering two. What RL can take from this, that is a tough one to think about. I think probably one of the things that could be used, I think it's already sort of used in many post-training algorithms, is just the specific validator, the verifiable rewards that can be given. But it's already out there, so it's nothing new that I'm mentioning. I hope that answers the question.
No, but I do believe that there are some maybe other advances that you introduced that the RL community should adopt. Maybe it's a matter of advocacy, right? But yeah, you did a great job here. So thank you.
Thank you, Lior.
Okay.
I'll ask.
Sorry, wait.
Sorry. Yes, I would like to ask a question, maybe a little bit of detail. When you describe your S1 and S2 reasoners, you gave references to them. Could you please describe for someone who's not an expert on those two systems some of their characteristics in a qualitative manner?
So was everyone able to hear Dr. Waltota's question? I hope.
No, it was related to slide 47, 46, 46 and 47. So you have, S1 and S2 in the, the S2 solver, the S1 solver, and I wonder whether, again, you could give some qualitative explanation of the differences.
So I think this actually relates back to RQ2, right? And that is our original SOFAI architecture. It again comes back from the theory of thinking fast and slow. So the idea is when you get a problem, right, you immediately think. So, if somebody says me 2 plus 2, I would not have to think for 5 minutes and answer, oh, no, it's 4. It's 2 plus 2, 4. It's a reflex. So that's the whole idea of S1, something that's fast, give you a quick answer, a quick candidate answer. It need not be always the correct answer, but a quick candidate answer. That's the whole idea of S1. For S2, it's something like a reasoning model, as we say here. So more deliberate thinking, slow thinking. So, if somebody is asking me, how can you integrate under or differentiate under the integral sign, I would have to think a lot about it. It's not something reflects to me. So that's what the characteristic of S2 is, a reasoning model that can reason and think a bit more deliberately about the problem and then give an answer. It's not supposed to be always it's not supposed to always give the right answer, but in a single pass it's supposed to perform better compared to S1. So that's the whole idea. Something that's more deliberate is and slow is what our S2 is. Something that's fast and quick to give us an answer is what S1 is.
So to follow up, you could replace the S2 solver with a different one. So there is a trade-off there as to how deep that goes, how first principle based it is. And you have a choice here. It says DeepSeek R1 8P with thinking. Why did you choose that?
Right. So I can answer that. So this was particularly for running experiments across models which were less than 10 billion or so. The idea was we were trying to see if through this architecture itself, can we move the performance or push the performance past what bigger models are doing by just iterating with targeted signals of what's actually wrong. So that was the core idea of sort of using smaller models. Another reason was the compute that we had to run the experiments. But again, I mean, I do not have that slide here, but during my proposal, I did discuss about, 1 second. So this discuss about this architecture where we had, instead of an S2 solver being an LRM, we had it as a symbolic solver, degree of saturation with backtracking. And there, again, as you mentioned, right, the trade-off was for a symbolic solver like that, it's sound and complete. So we did not have to add another solution evaluator there in that scenario. But just to mention, yes, you're right, that trade-off would work. And yeah.
Thank you for bringing that back.
Vedant, why don't you put up the title slide? I just want to get your photograph with your committee. They are all showing up in my thing at the top. Right. So committee members, please look into the camera just for 1 second. There you are. Okay, so we got that thing. Well, let's see if others have question. I have a couple of later on. Vignesh, you want to ask anything?
I just wanted to ask later, but I can ask now. So it's a general question. So I was wondering, Vedant, if you thought about your first takeaway. I'm assuming that this classification of can you restate it in terms of learning paradigms like supervised, unsupervised reinforcement or semi-supervised? If you go to the first takeaway, you have this correctness signal determines placement, right? can this takeaway be stated in terms of the learning paradigms, or it is independent of it? Have you thought about it?
I
Does
mean,
it even make sense?
right. I think I haven't thought about it, but thinking about it, just by going off of if you don't have the ground truth label, it would generally mean that you are going for something like a unsupervised learning. If you have, a partial check, as I talk about, for that you'll go for something like semi-supervised. And if you have the actual verification, a ground truth label, you'll go for supervised learning. How would that actually map to the way I've placed it here and the different RQs and their takeaways? I haven't really thought about it.
Because those learning paradigms are only used for only in the context of training they make sense. My understanding is these correctness signals is more important on during the inference. So I don't. I'm wondering whether this takeaway would translate to learning paradigm or not. I'm not sure. The other common or the compositionality, right? So when you compose these placements, right, that places bigger. Uh, so, for example, in your experiments and the test cases, there is a reason why these composing these placement avoids contradictory response. They go well with each other because their failure modes are independent, right? So,
Right.
uh, so uh, uh, I think it will be useful to make those make it as a clear assumption in your document if it is not already there.
Understood.
Yeah, those are the two comments I had.
Thank you, Dr. Vignesh. But yeah, I mean, that wasn't exactly by choice, but how it turned out to be. But certainly it's something what would happen when they are not complementary to each other is something not yet tested.
So they may not be complementary in this simplest case where their failure modes are not independent. They are dependent. For example, if your verifier is actually checking the output based on the status of the fault, and the fault is provided as input, right? So then there is a dependency. When there is dependency, they can create problems.
Right.
Do you see what I'm saying?
Yep, I got that. Yep. No, that makes sense.
So that's an assumption, right? So that
Yep.
needs to be stated if it's not already in there.
We'll make sure that's there.
Okay. So for me, go to that four, taxonomies that you earlier presented about neurosymbolic kind of thing.
This is the one, right, Dr.
Yeah, this one. So, what in your through your investigations, what did you learn about this? Which one fits the investigation you did, and what did you learn about practicality of any one of these fitting into the kind of thing you are trying to do?
Right. So I think I can answer that from this slide itself, Dr. here. So this is, what I sort of talk about as different places in the four places where symbolic can enter that I mentioned is before learning, at the input, at generation, or after generation. So for the first taxonomy, it directly links to generating training data, the hypothesis set, the learning algorithm, training it, and the final hypothesis or the output. For depths of infusion, if we want to talk about, it would not really focus anything on before learning, but at the input, what you do is shallow. At generation, what I do is semi-deep and deep infusion, and there is nothing specific for after generation. Then for couch, I've like mentioned here symbolic, neurosymbolic, symbolic, bracket neurosymbolic, symbolic to neurosymbolic, inside nested neuro, and these are the different ways how the six architectures that COTS discusses refers to before learning, at the input, at generation, after generation. The 15 design patterns that were there for the last one, they were just solely design patterns as to how would you link or how would you really just train it. So they can be modified and can go into either of these before learning, at the input, at generation, and after generation. The specific distinction
Which
there
one?
have.
Yeah, but rather than conceptual, which one actually helps you architect a solution, build a system?
I mean, the most general one here and the easiest that I can quickly relate to all my RQs would be COTS. COTS 6 architectural coupling. That is very easily. I can also define how shallow and semi-deep links to what I've done, but COTS is the most easiest for me to quickly link to how I've defined the correctness signal and the placements.
Okay. And uh, how do you map this into issue that currently, um, you know, I find very important, the 14 foundational elements for building enterprise systems.
Mhm.
What did you learn here, let's say for alignment or for grounding
Mhm.
or for explanation or any of those things that while you chose these three, retrieval, planning and reasoning, what did you learn or what insights you might have uh, along the line of building the robust enterprise class AI systems?
Right. So I think talking about those elements, Doctor, those elements then become, sort of the goal that we are finally looking at, right? If we are looking at goal for alignment or, reproducibility or explainability, that would lead to a specific type of correctness. Then you take that goal as what you want and check what existing systems can do. So maybe for something like grounding, can existing systems give you provenance or go back and tell, okay, you know what, this is where I got this data from. If they cannot, then that becomes a correctness signal, and that then links to RQ1. Similarly, we can think about different foundation elements as sort of goal for a certain task and link it back to the correctness checks and then to the placements. Because as I
Okay.
understand, those 14 elements are the system the system metrics as a whole, how well that system works in terms of grounding, alignment, and so on, and not a specific evaluation metric per se for a specific model or agent inside that system as we have defined it. So just to give a context
Now,
to everyone, there is work by Dr. Seth and students where they talk about C3AN system, where building C3AN system using knowledge and using different foundation elements across three pillars. So it's very brief, but there is a lot more to mention about that. But briefly, that's what Dr. Seth is asking me about.
yeah, I don't see your work, helping me understand the dimension of grounding or alignment or something right now. But we'll discuss later on. Okay, great. More questions? Anybody from the audience? They are still there. So far, only committee has asked questions.
Yeah.
Very nice to see Michael.
So I have a quick question.
Let me turn off my microphone. Will it pick it up there? Okay, or should we do the opposite?
I think now you can speak.
Thank you. So my question is a question of detail. You mentioned on slide 23 fault and violation. Okay. And I was wondering if you could explain the difference between fault and violation.
Slide 23. This is the one, right?
Yes. Maybe I am.
All
This slide near that instead. I may have done the wrong one. But at one point you seem to have a difference between violation, okay, which you have at the bottom of this, what we said back on escalation, okay, and fault, which now I don't see anymore on the slide. So I'm confused.
fault would be here, but there isn't a specifically violation that I mentioned.
No, in that same slide, look at the bottom most sentence. If I'm not wrong, you have something.
Yes, slide 23. So
Okay. Yeah, I can got it. Thank you so much, Dr. Vignesh.
But one violation invalidates the whole answer, the full history, where the fault sits in one place.
Right.
So your violation and fault, are they the same thing? Are they same?
So here I'll quickly give a background of the domains, and that's where I refer to between faults and violation. Here, one of the domains or the problem that we tackle is graph coloring. So in a graph coloring, the problem is given a graph, given a number of colors. You have to color all the graphs such that no two adjacent edges are colored with the same color. So here in this case, even if you have a partial solution, a partially correct colored graph, but then there are some edges, which are connected with each other, which has the same color, those are the violations. So what happens there is, in these cases where you have these violations, but you still have the rest of them just correctly colored, that would still might not become a part of the actually correct solution. Why? Because by just handling this violation, you might have to change the entire solution itself. On the other hand, when I say fault, is linking it to the debug bench. So what debug bench actually does, it takes in the lead code problems and its solution, and in those actually correct solution, it inserts one incorrect fault anywhere in that code piece. So you can think of it, a simple problem of lead code is you have to write a program that can solve 2 plus 2. Right, you have a Python program that can solve 2 plus 2, and in that program, which is, let's say, 4 lines, it inserts a completely new variable name in the addition equation, and then it's going to give me an error. So that is the fault. That means here what I'm trying to say is, if you have seen multiple different ways of resolving that fault, and if you give all that information of all the ways of resolving that fault to reasoning model, it will perform better. Why? Because that fault is very local. We know everything else is correct. Only that one small part of the code, we don't know what part of it, but only one small part of it is incorrect. So after looking at all the different possible answers or tries of how it was solved and the feedback for it, it would help the reasoning model to localize that issue or that fault even more. So this is how I'm differentiating the fault and the violation. Violation here in terms of the constraints, fault here is in terms of the actual task itself.
Yeah, the example of attention is interesting because a lot of work has been done in the educational literature on modeling errors in addition by pupils, by children in school, and one way of trying to tutor children and create more targeted sets of exercises is to identify the fault really that the child is using. For example, not handling carry properly in additions, is an error, is analogous to a stuck error in a circuit or something like that.
Right.
When I think violation, it seems to me that I think more of breaking a constraint that is already there without any attempt to model what the misgiving is. The fault corresponds to a misgiving by the pupil, for example. And the violation is the pupil simply didn't do the right thing. So it is not as informative as explicit fault model.
I see. Okay.
That may be a difference you find in the literature, in some literature. I hope that makes sense. But thank you for the answer.
Thank you, Dr. Valterra.